Hello and welcome to FlowVision video series. In this episode we will model blood flow in a human vein during replacement of a stent. To do so we will use automatic body replacement feature of FlowVision in order to import different sized stents to represent the enlargement of the stent. Let's start by creating our project by using the vein geometry as the main fluid domain. And let's name our project as vein. So here, as you see, we have a simple cylindrical body, and then I will continue by importing different bodies which are initially we have a blockage in the initial position. Let's turn off the perspective projection and see from the Z direction, and as you see here we have a blockage, and then I will continue first by renaming this imported object as blockage initial, and then import another object which is the stent at initial position. Again, as you see here, it's the stent, and if you look from the Z direction, it's corresponding to the initial blockage position. And let's rename this file as stent initial. Now we should continue similarly as blockage half open. You may realize that for the blockage geometries we have some cylindrical region out of the cylindrical vein geometry, which is actually not a problem, because if you have a geometry or half of a geometry out of the computational domain in FlowVision solver will ignore that part, so it's not a problem. So here the important thing is that bumpy region which represents the blockage, so and we have it in the correct direction, actually, correct position. So finally we need this stent fully open, which is close to the size of the vein in diameter. Let's say stent fully open. So the basic idea is in the start of the simulation I want to use only the blockage initial and stent initial, and then at some specific instance I will remove these bodies automatically and superpose the flow and import blockage half, which is smaller than the blockage initial, and correspondingly the stent half, and finally we will have only the stent fully open. Now I will show you how to do this in the FlowVision project window. Let's start from the beginning and go from top to bottom in our project tree. Here I would like to just show the size of our domain, which is 4 millimeters in size, which is a typical size for a human vein. So let's continue by, let's first define some reference values, maybe if they are important, but here I will use the default values actually. And now I continue by creating a substance which I would like to call as blood, and which in this case I will assume as Newtonian, but keep in mind that we also use non-Newtonian fluid modeling and FlowVision, and in some cases we use blood as non-Newtonian. So here I will just simply give constant density and viscosity values. Once I have a substance, I need to create a continuous phase, which I can call the phase blood, and add the existing substance blood to this phase and define the physical processes that I would like to take into consideration, which is actually only the motion in this case is enough. Let's continue with creating a model and rename it in the same manner and add the phase blood to this model. Here at this point it's better to define some initial data. If we consider our body like this, in either way, let's look through X, and we can assume flow in positive Z direction. Here we need to define that. Here I will use, instead of constant, the formula editor of FlowVision, just to later remember what value I used here, because it's usually millimeters per second for blood flow values, but here FlowVision uses meters per second. So here I write 50 millimeters per second and divide by 1000 just to convert it into appropriate units, and click apply. And I will use zero pressure, which means atmospheric pressure in this case, depending on the reference pressure value. Okay, so I minimize these sections and I minimize the objects section also, and continue with the subregions. I have only one subregion, which I can again call subregion blood, and assign the model blood to this subregion. Here, subregion is the section where we will define the boundary conditions, and to do so, first I need to assign to the imported objects as moving bodies. This is under the menu modifiers. I say create modifiers. Modifier type is the moving body, and I will turn these imported objects, all of them, into moving bodies now. Let's start the blockage initial. It's the moving body blockage initial. And here the idea is these objects should be not permanently active, but instead they should be active only once by time, which I will give as for the initials start in seconds 0 and duration in seconds 0.03, which is 30 milliseconds. Then for the since these bodies will not move, also we can just say update is disabled, say apply, which will increase the speed of our solution actually. Then I will continue by creating other moving bodies. Next one is the Stent initial. Let's change his name. change the activation to only once by time. Again, starting second 0 and duration is 30, and update is closed because it will be in the same location, but it will not be existing there all the time during the course of the simulation. So now I have the blockage half open. Actually, here what I'm doing is the most critical part of this simulation, and as you see, it's just very simple setup for the user. And for the half open blockage and Stent, I use these values. Of course, here, as you get the idea, you can use a lot of geometries, a lot of stages, not like me here. I did only 3 to make it easily understood during a live demonstration. But of course, you can use as much as you want, different Stent initial positions, second position, third position, like that. And you can use different appearing times and duration of appearances. So now the last one is the Stent fully open, which starts in seconds 62, and the duration is same with the others, 30 milliseconds, and I again disable the update. So let's give the name here also, moving body, Stent fully open. Okay. Now the next thing is to check and modify the boundary conditions. FlowVision already has some boundary conditions defined for me. Let's check them. 0 for all the surfaces, which actually is not exactly what I want, and then we have boundary conditions already assigned for the bodies. Okay, let's first start by naming those. Let's say the boundary condition blockage initial, boundary condition Stent initial, boundary condition blockage half open. You don't have to give names for all of those, but assuming you will use more than 5 bodies, I would hardly recommend you to give names in order to avoid confusion during the project. So here I just give those names, and then also I just want to show you to make sure that those moving bodies have the correct boundary conditions. You can just right click and say for example, for the Stent initial, you can say the boundary condition Stent initial. For the blockage half open, and you can do the same for all of them, just to make sure. And later, as you remember, we had one boundary condition for these 3 surfaces, but actually we need 3. Let's create 2 more and say if this is the inlet, let's say the type is inlet, and let's say we will define the normal velocity with pressure. Then we need some Wayne walls, and finally we need an outlet, which will have the type free outlet. And now I will go to selection mode and select these surfaces. This is inlet, which is correct. This should be the way in walls, and finally this should be the outlet. Now I will have a final look and check these values. Like for inlet, for example, it's normal velocity, so I need to define the same numbers I used in the initial conditions. That's all. And for wave walls, it's a wall with no slip condition, and the outlet, it's free outlet with atmospheric pressure condition. Then all we need to do is to generate a grid and continue our simulation. So let's go to the initial grid section and open the initial grid editor. Here in X and Y directions, I will use homogeneous grids with 0.2 millimeters size. So it's, as you see, it's 0.2 millimeters, and it's the same size from the very left to the very right of the x-axis, and for the y I do the same. And finally, for the Z direction, what I'm going to do is, as you see, we have the stance here, so I will place two reference lines to the left and right of the stance, and I will have the minimum sized initial grid elements here, and the sizes I will use is here, similar to other axis, 0.2 millimeters, and as the maximum value I will use 1 millimeter in the left and right boundaries of the Z direction. By doing so, I will have something close to 40,000 cells, but this is only the initial grid. So what we have is actually later we will have, let me just show you initial grid very quickly, and later we will have closer look at this grid with the adaptations, also local adaptations. So in addition to the initial grid, what I'm going to do is I'll go back to the boundary conditions, and using the stents I will activate some adaptations here. I will use first level of adaptation with 2 stratas, which means 2 layers with adapted sizes in the vicinity of the boundaries. So I will do the same for all stands. I have 3 of them here. This was the whole process I need to follow for grid generation. So let's minimize all of our tree. Let's go to the solver section, and for the time step, here I will use simply a constant time step, but FlowVision has a complex adaptive time step mechanism which will be covered in different episodes of the video series, so that's enough for this case. And also we can add some residuals to monitor during the course of simulation as plots. Okay, so from now on I would like to start a solver and run a case. Here I will do it just on a 4-core laptop, which will be enough to make the simulation. So now I'm connected to solver, which means I'm ready to start the simulation. So let's do that, and once the simulation is started, I'll as FlowVision warns me, I need to enter two values here to be able to make the calculations for the substance properties. Okay, and then let's click start computation again from the beginning. Now what I'm going to do is, while the FlowVision starts the calculations, I will make some post-processing and try to show you what we've been doing. So better to have these windows a little bit smaller. Okay, as you see, the calculation started. So here I already have one plane for post-processing, which is a recommended plane to use. So let's start with first checking the grid as a section here. So to see it better, I can make this plane as a clipping object, and here all the solids as clipped. So what I have now is the computation grid initially, and let me also turn off the surface fill, which will leave me with only the grid. And also let's hide the plane. So here, as you see, this is the grid at the 9th step, for example, which is being used. As you see, we have it's a section, of course. We have the blockage, and we have the section of the initial stent, as you see here. So let's hide this one and continue creating other layers to further understand and investigate the blood flow. So I create some velocity vector layers in the same plane, as you see here, from left to right in the positive direction. It goes on like this. So we can unhide this one, and we can look it together with the stent initial, or similarly with the computation grid section in this region. This is the main idea. Maybe we should also create one more layer like the color contours with maybe let me show you the pressure, and let's open a legend there. And as you see, once one more step has passed, we can see those values and the layer on the graphical user interface. And now as we are coming close to the 30 milliseconds, now what's going to happen here is the replacement of the body. As you see, it's now not the stand initial, but the stand half open. Now I will show you again what we have. Stand initial is here, and previously we had here the holes, and we had here the blockage initial, which is slightly down, but now we have the blockage half open as the geometry used, and we have the stand half open as the geometry used in this case. And of course the corresponding flow field is changing, and the pressure distribution also is the same. This is the main idea, and at the time 0.06 also this half open stand will be gone, and the fully open stand will be activated automatically, and also that blockage half open, this one will be deactivated. So here we won't have a blockage, but instead we will allow the blood flow to go through that region. So if we repeat ourselves, what we have done up to now is we define the typical internal flow fields with an inlet, the walls, and an outlet, and in the fluid domain we inserted 5 different imported objects, and we defined for them different time periods to be activated and deactivated. So this is being automatically done, and the flow field is superposed automatically once the one geometry is deactivated and disappears and the other comes into action. This is the idea here. And now I also would like to show you, while we still have 10 more steps, what we can do with the grid adaptation. Here in the beginning we said that we can make some adaptations, and in order to make this calculation as fast as possible I just omitted them, but now I would like to, for example, stand half open, which is active now, I would like to activate some adaptation as we did in the beginning, but I didn't activate them. And I would like to show you how this affects the grid and how it's automatically done. And also, this is the stand half open. Let's also make the same for stand fully open. Let's say this is also enabled, which is not active at this moment. So I just click Start Computation again, and this time continue my calculation from the step number 49. So here, as you see, I have some automatic adaptation of elements. Still, I have a very small cell count, so of course you can use much more than that, and which means much more accuracy in your calculations. Here I just would like to show you the main idea how we deal with these kind of things. So now we have almost 2 times of the initial elements. Yes, and just in a couple of like 10 steps we will have the final geometry and we will be finished with this work. So as the final words, let me close this one and show you, which will be automatically changed soon. So we modeled blood flow in a vein, and we use different stent and blockage geometries. We imported them from the beginning to FlowVision, and we defined their activation and deactivation times. So you can use this with not couple of but a lot of different geometries, activated and deactivated at different times. This is possible, and also as we describe in different mediums, it's also possible to run this simulation as a fully two-way strongly coupled fluid structure interaction case where the stent is deformed by means of blood pressure and by means of external forces or press stresses. That's all possible. And the idea is in all those cases, FlowVision still behaves those bodies in that case not moving but deforming, similar to what we have been doing here. So the same ideas apply. Like for example, what we've done with the grids, like we said, we can adapt elements around bodies. Here we adapted elements around the this stent body. As you see here, it's passing through this place, and also we will have the same adaptation with the fully open stent, which is not active at this moment but will be active in a very short time. This is the main idea here. So we're very close to the time step number 60. So if you have any further questions on this, please contact us at CapVidia or your local reseller, and we will be pleased to discuss details of this work and further enhancements that's possible on this task. Now, as you see, we're coming to the final step, and we're expecting this body to automatically change depending on the initial configurations we have made. I think it was the '62, I guess, for the half blockage, half open to disappear, and also the stent half open. These sections to disappear and the stent fully open to come into action. Yeah, here as you see, automatically the body is changed and the flow is superposed. Of course, the more stages you use, the more accuracy you will have in your calculations. That's obvious. So here, for example, in this case, the flow is trying to trying to adapt the new geometry. So this is also, as you see, we have the adaptations used here. Okay, thanks for watching and hope to see you in another episode of FlowVision CFD video series.